Hi, good morning to everyone. Myself K. Shivse. I'm from Mechanical Department. Our topic is on heat conduction equations in spherical coordinates. Introduction. The heat conduction equation in a spherical coordinating describes how the heat is transferred in sphere. It is a fundamental equation in heat transfer analysis for systems with spherical symmetry. Understanding these equations in equation is crucial for designing efficient heat transfer systems. Radial conduction through hollow spheres. Heat conduction through a plane wall. Q equal to T1 minus T2 by L by Ka. Heat conduction through a hollow cylinder. Q equals to T1 minus T2 by Ln R0 by Ri by 2 pi Kl. Heat conduction through a hollow cylinder. Q equals to T1 minus T2 by R0 minus Ri by 4 Kl R0 into Ri. Importance of spherical coordinates. The spherical coordinates are essential for systems with a radial symmetry, such as sphere or shell. They define a point in a space using a radius, polar angles, and altitude angles. The heat conduction equation in spherical coordinating accounts for a unique geometry. Spherical coordinates x, y, z axes r equals to radial distance, 0 equals to azimuthal angle, phi equals to polar angle. Inserting coordinates x equals to r sin theta cos phi, y equals to r sin theta sin phi, z equals to r sin theta. Heat conduction equation in spherical coordinates. The heat conduction equation in spherical coordinates is derived from four laws heat conduction. Fourier's law of heat conduction. If equations of heat flow in radial direction as well as variation in temperature along the radius, the equation is partially differential equation that describes the heat transfer within a spherical systems. General heat coordinating equations called heat conduction equations. Rectangular coordinates. Rate of heat conduction at x, y, z minus rate of heat conduction at x plus delta x, y plus delta y, and z plus delta z plus rate of heat generated inside the element equals to rate of change of energy content of the element. Qx equals to minus k dz dy delta t delta x delta t by delta x. Qy equals to minus k into dx into dz into delta t by delta y, and qz equals to minus k into dx dy into delta t by delta z. The value of elements qz, delta x, delta y, delta z, and coordinates of x, y, z axis of spherical element. Spherical coordinates. Fourier law in spherical coordinates. In spherical coordinate, Fourier's law relates to a heat flux to the temperature gradient. The heat flux factor is a function of radial, polar, and components. This law forms the basic for deriving the heat conduction equations in spherical coordinates. Fourier law of heat transfer. The heat flux is proportional to the temperature gradient. Q by A equals to Q minus K, where K equals to thermal conductivity, a measured of how fast heat flows through a material, K into T, but we usually use the value of average temperature. Q can be a X, Y, and Z components. It is a vector quantity. In most particles situations, convections, and radiations appear in combinations. Q equals to minus K into A delta T by delta X. Q by A equals to minus K into delta T by delta X. Here we can see the hot wall, the dt by dx, and a temperature profile, cooler wall. Thermal conductivity in spherical coordinates. Heat conduction analysis through three-dimensional heat coordinating systems in spherical coordinates. 1 by gamma into dou square by dou r square into rt plus 1 by r square sin theta into dou by a into theta into sin theta dou theta by dou t plus 1 by r square sin theta into dou square t by dou phi square minus q by k equals to 1 by alpha into dou theta by dou x. In thermal coordinative in spherical coordinating represents the material ability to conduct heat. It is property that varies with the temperature, pressure, and material compositions. In the heat conduction equation, the thermal coordinative terms influences the rate of heat transfer. Heat conduction equations derivations. A spherical coordinating r theta pi alpha equal e into 1 by r square into dou by dou r into r square dou theta by dou r plus 1 by r square sin square theta phi dou square t by dou theta square plus 1 by r square sin phi into dou by dou phi into sin phi into dou theta by dou phi plus q by pcp equals to dou theta by dou t by dou t plus vr into dou t by dou r plus v pi by r into dou t by dou phi plus v theta by r sin phi into dou t by dou phi. The heat conduction equation of differential. The heat conduction equation in spherical coordinate is derived by the example of Fourier's law and conservation of energy. In accounts of heat generation, convections, and radiations within a spherical system, the resulting equation in a second order particles, the differential equation with a respective temperatures. Boundary conditions in spherical coordinates. Temperature distribution, heat diffusion equations in a r direction of steady state condition with a no energy generation. 1 by r into d by dr into kr into dt by dr equals to 0. Fourier's law. Qr equals to minus k into dt by dr equals to minus k into 2 pi rl by dt by dr equals to constant. Boundary conditions t into r1 plus t into SL or t into R2 equals to t by t equals to T2. The temperature profile assuming the constant K. T into R equals to TSL minus TS2 by ln R1 by R2 into ln R by R2 plus T2 TS2. Logarithmical temperature distribution. Boundary conditions in spherical coordinate systems specify the temperature distribution at the boundary of sphere. They are essential for solving the heat conduction equation and determining the temperature profiles. Common boundary conditions include the precisible temperature, heat flux, and system coordinates. Solution techniques for heat conduction equation. Dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus Q by K equals to rho C by P by K dou T by dou T. T into K tau equals to T1 plus Ti minus T1 4 pi by differentiation of infinity n minus 1 into 1 by n. The heat conduction equation equals to sine into n pi x by 2l. Solving the heat conduction equation in spherical coordinating often require numerical methods. Finite difference, finite elements, and finite volume methods are commonly used for solving the complex problems. Analytical solutions are rare due to the non-linear nature of the heat conduction equations. Applications of heat conduction in spherical coordinate systems. The heat conduction equation in spherical coordinating first applications in various fields including engineering. It is used to model a heat transfer in planetary bodies, nuclear reactors, and heat exchangers. Understanding the heat conduction in spherical coordinating is essential for optimizing the thermal systems. Conclusion. The heat conduction equation in spherical coordinate is a powerful tool for the analyzing heat transfer in the system with radial symmetry. It accounts to a unique geometry of a spherical coordinating systems that provide insight into a temperature distribution. Mastering the equation is a key to design the efficient and effective heat transfer systems.